Hi Israels. So we're going to be doing subtopic 3.3 now, aldehydes and ketones. So let's first of all get this thing working because it looks like it's going to freeze up on me. Probably should have done this beforehand, but it wouldn't be a very exciting video if I didn't have something stuffing up. Okay, let's go from there. Now, aldehydes and ketones are related functional groups. That's why they're in the same subtopic together. And we're going to start with the arguably more simple of the two, which is an aldehyde. So aldehydes, they have the suffix, so the ending of their, the name of their molecules as al. Actually, what I'll do is I'll use this to start with. So we have the suffix al, and that replaces the e at the end of our base name. So for example, pentane changes into pentanal. Now, for it to be an aldehyde, we have to have our C double bond O, and we have to have at least one hydrogen attached to the carbon of that carbonyl group. So carbonyl group is the C double bond O, and there must be at least one hydrogen. There can be two, or one particular molecule, but there has to be at least one. So here is a list of some of the smaller ones. So we have methanal. So we have only one carbon in our aldehyde, and as we have only one carbon, there's no others that carbon is attached to. So we have two hydrogens on the end, so attached to that carbon. Now, once we move up to ethanal, so we have ethanal, which is from our two carbons here. And because it's an aldehyde, we have a hydrogen at the end here. Now, I did do the extended structure for the first two, so where we have all the carbons and the hydrogens, but for the remainder, the way I've drawn them is the line structure without any of the carbons. Now, you can see the hydrogen on the end. I've done that for illustration purposes. You can have them, you can also neglect them, that's fine as well. Regardless, the naming scheme is the same, very similar to the previous types of structures, where the number of carbons in the main chain dictates that base name, and then you can have the substituents off of it from there. Now, one important point here is that we don't have any numbers in these names. Now, the reason is because aldehyde, or the aldehyde groups, they are at the end of the molecule, and they have to be at the end of the molecule because this carbon here is attached to a hydrogen on one end, and that means it can't continue. It stops right there. And apart from this bond to the oxygen, there are only two other bonds on that carbon. So one side continues because it's attached to carbons, the other side is attached to a hydrogen, so it must be terminal, it must end. Now, once we get down here, we're going to look at naming the some more complicated branched ones. So I'll change my pen over to blue, and we are going to try and name this one. So actually, you know what? I'll go back to the laser for the start. So we first, the exact same thing as normal. We have to try and find the longest chain. More importantly, it's actually the longest chain that includes the carbonyl carbon. So this carbon here has to be part of it, because this is the highest priority functional group in this molecule. It's actually the only functional group apart from our alkene alkyl groups. So we have to include this one, and that is going to be our carbon number one. So actually, you know what? I'll go back to our pen, and I'll start numbering. Sorry. This has to be carbon one. We have to start at that group, or the carbonyl group. That makes this number 2, 3, 4, 5, and 6, and 7 here. Now, the important bit, I deliberately drew this molecule this way to make it a tiny bit trickier. If you say that the 8th carbon is the one down and to the left of this 7th, you would unfortunately be wrong, because that is actually not the longest carbon chain. We have to go up in the way I've drawn it. So we have to go up because that, even though it's been rotated and it's sticking up instead of in our zigzag pattern, it is still the longest chain. Now, funnily enough, now that longest chain is 9 carbons long. You don't actually have to be able to name these from scratch, but we're going to do it anyway. It's not any more difficult than the other ones, I don't think. So the base is 9 carbons, so it's going to be nonanal. So the highest you'll need to go to is oct. So for example, if it was 8 carbons in the main chain, it'd be octanal. But nonane is our 9 carbon alkane. So we modify that and chuck the Al at the end, removing the E. So nonanal. It does have two substituents though. Yeah, both of them are methyl groups. So we have 2 methyl groups, so we know we'll be saying dimethyl at some point. And we also have to, so I'll just chuck that here, dimethyl nonanal. We have to then include 2 numbers to show exactly where those methyl groups are. So there are sticking on carbon 2 and carbon 7, so it is 2, 7 dimethyl nonanal. Now again, you don't have to worry about anything apart from octanal, or sorry, a bit larger than octanal as the main chain, but you can expect multiple methyl groups or ethyl groups on whichever carbon chain they're giving you. Now, while we're here, we can name this other one where there's 2 aldehyde groups. So there's one at the ends. Now, as I've said in this bit here, the terminal hydrogens, the hydrogens on the end, they can be drawn, your molecule, your aldehyde can be drawn with those hydrogens, as I've done here, or without them, as you can see for this molecule with 2 aldehyde groups. Doesn't really matter. I mentioned it above earlier as well, but either way, they can be drawn both ways, so you have to be able to recognize them. So, naming this one. Now, because we have 2 aldehyde groups, it is going to be a dial. So just like if we had a diene or a diene or a diol for our alcohols, dial is what we're going to be using here. So it is going to be dial at the end, and then we have to consider what the longest chain is. So it'll be, let's just name them here. It doesn't matter which side we start with, but if we start from the left, 1, 2, 3, 4, 5, 6, and 7. So if we go back to our blue, this is going to be heptane. Oops, I don't know why I've done it like this. Let's see if I can make it look a bit nicer. Oh, barely. If anything, I just made it worse. Let's just get rid of the whole thing. There we go. Heptane dial. Now we did have to include the E back. So just like our dials, if we have our suffix being changed from beginning with a vowel to a consonant, so instead of al, it's dial, we need to add this this E again. So in this particular case, we have our heptane dial. Now there are no numbers, again, because even though this is carbons 1 and 7, while I'm here, I might just refix these back up. While the carbons 1 and 7 are the ones that are part of this aldehyde, they have to be at the end. So in other words, if it's heptane dial, the aldehydes must be at each end because they're both terminal. You can't have 2 of them down one end. Doesn't work like that. So you have to have them both at each end. So if you've got heptane dial, this is the only version or the only structure you can draw. Now, when we get down to here, ketones are similar in that they're made of a carbonyl group, so the C double bond O, but the difference is that the carbon that is part of that functional group has carbon atoms or carbon groups on each side. So we cannot have a ketone that is smaller than propanone. The reason is if it was any smaller, there would only be 2 carbons, and the carbon that is included in that C double bond O, the carbonyl, that would have a hydrogen here if it was any smaller. So propanone is our smallest. It has 3 carbons, 1, 2, 3, and our C double bond O must be in the middle. If it wasn't in the middle, if it was on one of the ends, then it would not be a ketone. Now, before I continue, the suffix is -one, as you can probably imagine, but instead of al for aldehydes, it'll be -one for the ketones. Okie doke. Now, because for propanone at least, the carbonyl group cannot be anywhere else, we don't bother with a number. Similarly, with butanone, if our C double bond O was here, or if it was here, it would be identical. And those are the only 2 places that it can be. It cannot be on the ends, so again, butanone does not have a number. Here or here are the exact same structure. Once we get higher than that though, so once we get to pent, we have 5, this is where there becomes a choice. So I've drawn the 2, so pentane 2-one and pentane 3-one. Those numbers are telling us on which carbon we have our ketone or our ketone group or our carbonyl group. And so if we name it 1, 2, 3, 4, 5, then we obviously have it on carbon 2. If we start from here, 1, 2, 3, 4, 5, we have our carbonyl group on carbon 3, so we have pentane 3-one. Now I've got a little bit of a question here. Probably should be able to work it out. Sorry. Can pentane 1-one or pentane 4-one exist? Now, hopefully, after what I mentioned before, pentane 1-one would imply that our C double bond O is on this end, in which case it would not be a ketone anymore, it would be an aldehyde. And pentane 4, if it was here instead of where it is there, pentane 4-one does not exist, because if the carbonyl group was here, we would start our numbering from the right instead of the left, and it would be pentane 2-one. So pentane 4-one cannot exist, neither can pentane 1-one. This one because it would be an aldehyde, and this one because it would be, if it could exist, it would be identical to pentane 2-one, and we always use the lower number if we have a choice. Okay, so we have a rather complicated looking molecule here, so let's work it out and hopefully I don't mess it up. Might have been a while since I drew this one. Okay, so you know what, I'll start with the red so I can number my carbons. So I'm going to start from the right, and the reason is because that will minimize the number for the ketone itself. So we have 1, 2, 3, 4, 5, 6, 7, 8. Thankfully 8 is the longest chain. Now again, I'm starting from the right to make the ketone or the carbonyl group on the lowest numbered carbon. Everything else just falls out from there. That makes this, so I'll do it in blue, this makes this octane 3-one. So octane 3-one is the base before we consider any of the substituents. Now, once we do have to consider the substituents, we see that we have 3 groups hanging off this one, 2 of which are methyl groups. So the one on carbon 2 and the one on carbon 5 are both this one here and this one here. They're both methyl groups. And this one on carbon 4 is a 2-carbon ethyl group. Now, when it comes to naming, we name alphabetically, so we'll put an ethyl group before the methyl group. But as I'm writing this name from right to left, I'm going to write the methyl groups first. Because there are 2 methyl groups, we're going to say dimethyl. There we are. So dimethyl. So it is dimethyl octane 3-one, but if I ever say dimethyl, I have to say exactly which carbons those are on. So we go 2 and 5 dimethyl octane 3-one. If there was no ethyl group on the carbon 4, that would be the structure. Also, that would be the name for the structure. But we are not almost finished, but we need to add in that 4-ethyl part. So 4-ethyl 2,5-dimethyl octane 3-one. Again, I deliberately chose a complex one here so that it covers all bases. If you have a simpler one, it should be easier than this. So scrolling down. So let's look. If we have multiple keto groups, we have a similar deal here. So as it says, it follows the same rules as aldehydes in that we are going to name it as a dione. The difference here, though, is that we will have numbers because these are not just at each end. They could be anywhere along a chain if it's long enough. So I probably shouldn't have actually said it. Multiple keto groups follow the same rules as the aldehydes because it doesn't. It probably should be more like the alcohols. Although even then, alcohol, the OH group can be on the ends, whereas this one cannot. Otherwise, it would be an aldehyde. Either way, the ketones are their own thing because of where these ketone groups can be. So we have carbon 1, 2, 3, 4, 5, 6, and then 7. The reason why I'm counting from the right is to minimize the numbers that these carbonyl groups are on, the C double bond O groups are on. If I count from the left, that would be 5 and 6, which are obviously larger than 2 and 3. So once we get to naming it, we know it's going to be a dione. Now, if we have dione, there's going to be 2 numbers. Again, it wasn't the same for dial, but that's because they were at the ends. Dione, we definitely need 2 numbers because these carbonyl groups could be on carbon 2 and 4, 2 and 5, 3 and 4, 4 and 5, 2 and 6. Yeah, there's a number of options, so we have to be specific. It'll be 2 and 3. So 2,3 dione, and the base chain is our 7 carbon chain, which will make it heptane. Now the reason why it's heptane and not heptane is because the same reason as before, our suffix is now dione, which starts with a D, a consonant, so we replace that E at the end of the base name heptane. And that should be it. I don't know why I gave myself that much space in the blue highlighting, but it is what it is. Now that we've covered how we name them and the different namings for all the different ways these can be arranged, we have to worry about what they do. So if we scroll down a bit, we can see that there are chemical reactions that occur with these molecules, or these functional molecules with these functional groups, and we can differentiate between them. So if someone says to you, hey, I've got this container and it has either an aldehyde or a ketone, has one of the two, can you work out what it has? And the answer is you should be able to, yes. And that is because of a reaction that aldehydes can do that ketones cannot. So as we see here, if we take our aldehyde, which is our C double bond O group with a hydrogen attached, and we react it in acidified dichromate, then what will happen is that carbon here will be oxidized. So oxidized meaning it'll be attached to an oxygen group. In this particular case, we have OH being added. So essentially, we turn this aldehyde into a carboxylic acid, which is in 3.5, so we'll learn about it more then. Regardless, we've taken off this hydrogen and replaced it with an OH. Now, in acidic conditions, that's what we make our carboxylic acid. If we happen to do the same reaction in a basic conditions, alkaline conditions instead, then what happens is this hydrogen is pulled off and we end up with our carboxylate ion. Again, we'll learn about that later, but you just take that H plus off, or the hydrogen off, as a H plus, leaving O minus behind. Now, the reason why this can happen with an aldehyde is because the bond between this carbon and this hydrogen, while strongish, is weaker than a carbon-carbon bond would be. So if we have a ketone where we have bonds with carbons, those are not going to be able to be pulled off under these reaction conditions. That means when we put it in acidified dichromate, nothing will happen. So nothing will happen. And the important bit here is that we can tell nothing happens because acidified dichromate, when it reacts and oxidizes our aldehyde, it changes from an orange color, which is caused by the 6 plus chromium ions, into a green color, which is from the chromium 2 plus ions. So it goes from orange to green if it does a reaction. If you put it in with an aldehyde, it will do that. If you put it in with a ketone, it will stay orange because our chromium 6 plus ions will remain. So they will not react, they will not oxidize our ketone, they will not be reduced themselves from 6 plus to 2 plus. Now I've mentioned it here, so this dichromate does also oxidize alcohols, which I believe, if I'm not mistaken, we covered towards the bottom here anyway. Yep, we have it just here. So it oxidizes this, and as you can see, if we take our primary alcohol and we oxidize it with this acidified dichromate and we turn it into an aldehyde, this aldehyde can actually do this reaction again with the same stuff. So we take this aldehyde that is the product of this reaction and we can react it further to turn it into a carboxylic acid. Okay, now we have another way of being able to identify whether we have an aldehyde or a ketone, and that is something called Tollens reagent. So Tollens reagent has it's a mixture which includes silver ions, and when it reacts, the silver will reduce from a positive ion into metallic silver. So if you put it into an aldehyde mix or mix with an aldehyde in it, only aldehydes, by the way, it doesn't work with alcohols. If you put it with aldehydes, it will reduce the silver into metallic silver, and that's the reaction we use to coat our clear glass bottles and make them silvered like a little mirror, which we will do at some point this year. Now the final point is that ketones, they react neither with acidified potassium dichromate or Tollens reagent. So if we want to verify that we have a ketone, we can react it with both. Although, there'd be specific situations where Tollens reagent would be more appropriate, but you can have a think about that. And I think that's pretty much it for this subtopic. So good luck.